A recurrent negative polarity transequatorial coronal hole catalogued by solar monitoring networks as CH1366 has rotated into an Earth-facing position and its high speed. Solar wind stream is expected to begin arriving at our planet today, May 14, 2026, even as the magnetosphere has not yet fully recovered. From the glancing blow delivered by the coronal mass ejection launched from sunspot region R4436 on May 10th, the instruments are not showing quiet conditions. The instruments are showing a solar environment in active transition with solar wind speeds. Forecast to ramp upward again as this new stream reaches the L1 observation point, the gravitational balance point between the Earth and the Sun, 1.5 million kilometers in front of our planet, where NOAA's space weather follow-on Lagrange 1 observatory, which reached its final orbital position in January of this year. Now stands Sentinel. A slight chance of G1 minor geomagnetic storm intervals exists. That is the official language. Understand what it means. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources, NOAA's Space Weather Prediction Center, the SOHO spacecraft's LASCO imagery, EarthSky's verified solar monitoring summaries, SpaceWeather's coronal hole tracking system, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture, because what is arriving today is not simply a stream of fast-moving, charged particles bumping gently against the outer edge of Earth's magnetic shield. What is arriving today is one layer of a compound solar weather event, the confluence of CME aftermath and coronal hole stream that is the kind of stacked, overlapping disturbance that historically has produced effects larger than either event would have generated alone. The solar wind does not arrive clean, it arrives carrying with it the residue of everything that has already passed through this region of the inner heliosphere in the last 4 days. A prior positive polarity coronal hole high-speed stream came and went, its speeds rising and then declining back toward normal. Then on May 10th at 1319 UTC, sunspot region R4436, a complex, magnetically agitated region sitting in the northeast portion of the visible solar disk, fired an M5, 8-class flare, the strongest in days. A significant partial halo coronal mass ejection accompanied it, first appearing in SOHO's LASCO. See to coronagraph imagery at 1348 UTC. The bulk of that ejected mass was aimed east of Earth's orbital path. But CN-LIL solar wind modeling, the large-scale physics-based simulation of the inner heliosphere used by NOAA's Space Weather Forecast Office, identified a possible glancing blow arriving at Earth early on May 13th. If confirmed, forecasters said the KP index could reach 5, the threshold for G1 minor storm conditions. That strike may have been weak. The magnetosphere may have felt it only as a disturbance rather than a storm, but the interplanetary magnetic field in this region of space was already disturbed, already compressed in places, already seeded with the turbulence that makes a subsequent high-speed stream's impact unpredictable. And now, arriving on top of that unsettled residue, comes CH1366 and the fast wind it has been breathing into space for days. Understand what a coronal hole is. In the ordinary solar corona, the outermost layer of the Sun's atmosphere, a region that reaches temperatures of 1 to 3 million degrees Celsius, magnetic field lines loop back on themselves, constraining solar plasma in brilliant arch structures visible in extreme ultraviolet imagery from the Solar Dynamics Observatory. But coronal holes are regions where the Sun's magnetic field opens outward, extending out into interplanetary space like the open end of a funnel rather than looping back. The plasma from these open regions streams freely outward, uncontained, accelerated by the solar wind's driving pressure to speeds significantly higher than the ambient solar wind. The ambient solar wind, the background flow of particles constantly leaving the Sun, travels at roughly 400 kilometers per second. That is 1.44 million kilometers per hour. A high-speed stream from a coronal hole can push those speeds to 600 kilometers per second or more, and NOAA's own records of previous coronal hole stream arrivals confirm this. In a documented G1 storm triggered by a positive polarity coronal hole high-speed stream, solar wind speeds reached upward of 600 kilometers per second, and those increased wind speeds combined with a disturbed solar wind environment were sufficient to push geomagnetic activity to G1 minor storm conditions periodically through the day, 600 kilometers per second. To cross the entire breadth of the continental United States, roughly 4,500 kilometers at that speed, would take 7.5 seconds. What is coming today is not slow, what is coming today is not gentle. The hole itself, CH1366, is transequatorial in character. That word carries weight in solar physics. A transequatorial coronal hole straddles the solar equator, extending into both the northern and southern solar hemispheres simultaneously. This geometry is significant because the most geo-effective coronal holes, the ones whose wind streams are most precisely aimed at Earth, are those positioned along or near the solar equatorial plane, which is the plane closest to the ecliptic, the plane in which Earth orbits the Sun. A high-latitude polar coronal hole sends its wind stream at an angle, often missing Earth entirely or delivering only a grazing contact. A transequatorial hole, by contrast, projects its fast wind like a hose aimed directly down the ecliptic. The data from spaceweather's automated detection system recorded this hole in an Earth-facing position. The timing of its stream arrival, expected to begin today, May 14th, is consistent with the typical transit time from the Sun to Earth for a high-speed stream, which runs between 3 and 4 days from the time a hole rotates into direct Earth-facing alignment. And here is where this account becomes genuinely significant. What makes a coronal hole high-speed stream dangerous, not merely active, but genuinely capable of driving sustained geomagnetic disturbance, is not the speed of the wind alone. It is the interaction between that fast wind and the slower ambient wind ahead of it, as the fast stream overtakes the slower material in front of it. A compression region forms. Physicists call this a co-rotating interaction region, or CIR. The plasma in this compressed boundary is denser, more magnetically structured, and more capable of driving geomagnetic disturbance than either the fast stream or the slow wind would be on their own. NOAA's Space Weather Prediction Center has documented this in its own published science. High-speed streams plow into the slower solar wind and create these co-rotating interaction regions, and while the geomagnetic storms they drive are often less intense than those produced by coronal mass ejections, they frequently deposit more total energy into Earth's magnetosphere over a longer interval. Longer, that word matters. A CME storm can arrive fast, drive conditions to storm level quickly, and then subside. A CIR-driven storm associated with a persistent coronal hole high-speed stream can maintain elevated conditions for a day, 2 days, sometimes longer, because the coronal hole keeps feeding fast wind into space as the Sun rotates and Earth keeps rotating through the structure of that wind. Now bring in the second variable still lingering in the environment. The CME from our 4436 ES-M5, 8 flare on May 10th. That glancing blow did not simply pass and leave clear space behind it. A CME passage leaves a wake. The interplanetary magnetic field in the region downstream of the ejection is disturbed, tangled, carrying residual magnetic field orientations that can fluctuate between northward and southward in ways that are difficult to predict. NOAA monitoring data from the days following the M5-8 event showed precisely this. The B's component of the interplanetary magnetic field, the component that, when oriented southward, opens the door between the solar wind and Earth's magnetosphere, remained near neutral and variable. Small swings, not sustained. Not yet enough to drive a storm response, but the environment was primed. The solar wind had been disturbed, and into that disturbed environment, the transequatorial coronal hole CH1366 is now sending its fast stream. When a fast stream arrives and encounters a region already made turbulent by a CME's passage, the interaction can amplify the geomagnetic response. The system is not inactive, it is accumulating. Think about what a G1 storm actually means for the people living on this planet right now. On the NOAA space weather scale, a G1 minor storm is level 1 out of 5. It sounds small. It is the least severe rung, but what the official descriptions confirm is that even at G1, the aurora lovel, the circular band of atmospheric glow that rings Earth's polar regions, expands modestly southward from its usual position. In the northern hemisphere, aurora becomes possible across southern Canada, the northern tier of the United States, the United Kingdom, Scandinavia, and similar high-latitude regions. Power systems may experience minor fluctuations. Satellite orientation functions can be affected. Migratory animals, birds, whales, sea turtles that navigate using the Earth's magnetic field may receive slightly distorted signals. These are documented, verified effects at the lowest level of the scale. They are not catastrophic, but they are real, and they are a baseline, the lowest expression of a system that, when fully activated, has already demonstrated in recorded history that it is capable of shutting down the power supply for an entire province of 6 million people in 90 seconds. This is not a hypothesis. This is documented in the geological record and in the engineering logs of hydro. On March 13, 1989, at 2:44 in the morning, a powerful coronal mass ejection struck Earth's magnetosphere during an active period of solar cycle 22. The second of 2 sequential CMEs struck with a solar wind speed measured at an estimated 980 kilometers per second, carrying a southward interplanetary magnetic field component of 4260 nanotesla, conditions that overwhelmed the magnetosphere's ability to contain the energy being pumped into it. What happened in Quebec in those moments was not a slow deterioration, it was a cascade. 7 static VAR compensators on the Lagrange network tripped one after another. Without the voltage support they provided, voltage dropped to 0, 2 per unit on the transmission network. 5 high voltage lines too tripped through loss of synchronism. The James Bay network went offline in less than 90 seconds, cutting 21 gigawatts of supply. Quebec went dark. 6 million people, the entire population of a province, lost power. Schools and businesses shut down. The Montreal Metro stopped running during morning rush hour. The city's airport closed. Businesses that ran continuous industrial processes lost millions in damaged and wasted material. The entire blackout lasted 9 hours, and in some places longer. All caused by geomagnetically induced currents, invisible electrical flows driven into the power grid through the ground by the fluctuating magnetic field overhead. All caused by the sun. Think about the people in those neighborhoods in Montreal on that March morning in 1989. They woke in cold apartments. They reached for light switches and found nothing. They had no warning. Many, seeing the brillianter aura lighting up the sky and having never seen such a thing before, reportedly feared they were witnessing the opening moments of a nuclear strike. These were ordinary people, parents preparing children for school, shift workers returning from overnight jobs, hospital staff managing patients. The geomagnetic storm did not consult them before arriving. It did not ask whether the Montreal Metro was running or whether the aluminum smelters needed continuous power to keep their processes from seizing. It simply arrived, and the infrastructure collapsed before any engineer could respond. There are cities at similar latitudes today: Ottawa, Stockholm, Helsinki, Edinburgh, Anchorage, where the populations number in the hundreds of thousands to millions, where the power grids carry more load than hydro did in 1989, and where the underlying geology and transmission line geometry may present similar vulnerabilities. The question is not whether a storm capable of repeating 1989 will occur again. The question is when, and the geomagnetically induced currents do not restrict themselves to power grids. In Russia, the March 1989 storm caused automatic railway systems to report false blockages of tracks, disrupting the Gorky railway system intermittently for 3 to 4 hours. In New Jersey, the storm destroyed a transformer at a nuclear power plant. For U.S. Navy navigational satellites had to be taken out of service for up to a week, and the 1989 storm was not even close to the most powerful event the historical record holds. Go back further. Go back to September 1st and 2, 1859, and the event that carries the name of the British amateur astronomer who first saw its cause, the Carrington Event. On the morning of September 1st, Richard Carrington was in his observatory in Redhill, near London, sketching sunspots when he was confronted by a sudden brilliant white light erupting from the solar surface, the first recorded observation of a solar flare. Within 17 hours, a coronal mass ejection reached Earth, a transit that normally takes 3 to 4 days, accomplished in under 18 hours because a prior CME had already cleared the ambient solar wind from the path ahead, allowing the second ejection to travel through near vacuum at extraordinary speed. What followed was the largest geomagnetic storm in recorded history. Researchers estimate the DST index, the measure of the storm's intensity in nanotesla, reached approximately negative 1,760 nanotesla. The 1989 Quebec storm, devastating as it was, peaked at roughly negative 589 nanotesla. The Carrington event was, by this measure, approximately 3 times more powerful. Ice core samples from polar regions suggest it was at least twice as large as any storm in the preceding 500 years. On the modern NOAA scale, it would register as a G5, the highest possible level. The effects in 1859 were constrained only by the technology of the time. The telegraph was the critical infrastructure. Telegraph wires across North America and Europe surged with induced currents so powerful that operators received electrical shocks from their equipment. Telegraph paper spontaneously caught fire in offices across the continent. Some operators reported that they could disconnect their batteries entirely and continue sending and receiving messages powered only by the geomagnetically induced current flowing through the wires from the storm. Auroras were seen as far south as the Caribbean and Central America. People in the northeastern United States reportedly used the auroral glow to read newspapers at midnight. The infrastructure of the day was primitive enough that it failed spectacularly but not catastrophically because there was not yet enough of it to fail catastrophically. Now consider the difference. The United States alone operates a power grid carrying hundreds of thousands of kilometers of high-voltage transmission lines. The global satellite infrastructure includes approximately 10,000 active satellites. The global economy runs on GPS timing signals for everything from financial transactions to air traffic control to emergency dispatch systems. According to assessments by the National Academies of Sciences, a Carrington-scale event today has the potential to cost nearly $2 trillion in the United States alone, disrupting telecommunications, banking systems, GPS, and the energy grid. $1 trillion does not convey the scale in human terms. Think instead of the families in cities from Seattle to Warsaw who depend on GPS navigation to route emergency vehicles. Think of the hospitals operating on grid power. Think of the water treatment plants that pump drinking water using electrically driven pumps. Think of the 2 billion people globally who today live in cities. And now understand the mechanism that makes all of this possible. The bees, the southward pointing component of the interplanetary magnetic field. This single variable, a directionality measurement of a magnetic field carried by the solar wind, is the key that opens or closes the door between the sun's energy and Earth's magnetic shield. When bees is northward, it aligns with Earth's own magnetic field and the two systems largely repel each other. The magnetosphere holds. When bees turns southward, it opposes Earth's field, and at the point of contact on the dayside magnetopause, the boundary between interplanetary space and Earth's protective magnetic bubble magnetic reconnection occurs. Field lines from the solar wind merge with Earth's field lines. Energy flows inward. Current systems energize. The auroral electrojet, the enormous river of electrical current flowing through the upper atmosphere at polar latitudes, intensifies. It is this electrojet, fluctuating on timescales of minutes, that drives the geomagnetically induced currents into the ground below. The critical point is this: the bees measurement cannot be made with sufficient lead time from Earth's surface. The NOAA SUFO L1 observatory, now operational at the L1 point since January 2026, provides roughly 15 to 60 minutes of warning before an incoming solar wind structure reaches Earth, depending on speed. For a storm arriving at 600 kilometers per second, this means perhaps 40 minutes of warning between the observatory's first measurement and the moment the disturbance presses against the magnetopause, 40 minutes. In the modern grid, that is enough time for operators to take protective actions, raising trip thresholds, reducing reactive power compensation, coordinating with neighboring utilities, but it is not enough time to prevent all effects from a sufficiently powerful southward B's event. And at 600 kilometers per second, the question of what the B's will do when it arrives cannot be answered in advance with certainty. The models project, the instruments monitor, but the answer arrives only when the solar wind does. NOAA's Space Weather Prediction Center has its own framing for this uncertainty, and it is worth stating precisely. G1 storm intervals are possible today as wind speeds ramp up again. Possible, not certain, intervals, not sustained. The language is careful. Scientists choose their language carefully here, and that careful language is itself the warning. A confirmed G1 with sustained southward B's could produce visible aurora across the northern United Kingdom, across Scotland and northern England, across Scandinavia, across Canada's populated southern corridor. The city of Reykjavik in Iceland, population approximately 230,000, sits at a magnetic latitude where even a mild G1 expansion of the aurora lovel can put the lights directly overhead. The city of Troms in northern Norway, which has built an entire tourism industry around her aura viewing, sits so deep within the normal auroral zone that its residents measure geomagnetic activity not as a curiosity but as a routine feature of the sky. But these are the populations adapted to living with this environment. The people who are less adapted are the ones in cities that have never seen the aurora before and whose infrastructure engineers may not have stress-tested their transformers for geomagnetically induced current scenarios. The people in the city of Atlanta, Georgia, which sits at a latitude where even the May 2024 G5 storm pushed the aurora to visibility, whose power grid was not designed with polar substations in mind and whose population had never experienced an electrically disruptive geomagnetic event, they matter in this account too. Now connect the threads that run beneath the surface of today's event. R4436, the sunspot region that produced the M5. 8 flare on May 10th was already active on the far side of the Sun before it rotated into Earth's view. It had already produced multiple CMEs before becoming visible in Earth-facing coronagraph imagery. When it emerged and fired, the Type 2 radio sweep detected at the time of the flare confirmed a CME launch and provided an estimated eject a speed of 650 kilometers per second. The blast caused an R2 moderate radio blackout. High-frequency communications disrupted across the sunlit Atlantic Ocean, affecting transatlantic pilots, mariners, and amateur radio operators, and R4436 is still active. Solar physicist Patricio, observing from Santiago, Chile, noted in publicly shared imagery from May 11th that both R4432 and R4436 carry gamma-delta magnetic configurations, the most complex and energetically volatile classification a sunspot group can carry, associated with an increased probability of producing major eruptive flares. R4436 is rotating toward more direct Earth alignment. The next eruption from that region, whenever it occurs, will be aimed more directly at our planet than the May 10th event was. NOAA confirms that both R4436 and its neighbor R443 remain capable of producing M-class and possibly X-class eruptions. The radio flux index from spaceweather, CALM as of May 13th, sits at 111 solar flux units, an elevated value consistent with an active solar disk. The Sun is near the peak of its 11-year solar cycle. Solar cycle 25 reached its smooth maximum on approximately October 11th and 12, 2024, according to data analyzed by solar activity tracking networks. This year, 2026, sits on the descending slope of that maximum, but history shows that the descending phase of a solar cycle is not a period of safety. Some of the most powerful individual events in space weather history, the March 1989 storm, the October 2003 Halloween storms, the May 2024 G5 event, occurred not at the peak of solar maximum but near it, on the active shoulder of the cycle. The system does not follow a smooth curve downward, it stutters. It produces isolated extreme events even as the overall sunspot count trends lower. In January 2026, Earth experienced the largest solar radiation storm in more than 20 years, rated as 4 on the 5-level severity scale. This year has not been quiet. This year has been proving, event by event, that a solar cycle past its smooth maximum is still capable of producing consequential space weather. And through all of this, there are now approximately 10,000 active satellites in orbit around Earth, more than at any previous point in human history, clustered in low Earth orbit by megaconstellations numbering in the thousands of individual spacecraft. A significant geomagnetic storm heats and expands the thermosphere, the upper atmosphere, increasing the drag on every one of those satellites, accelerating their orbital decay, and increasing the probability of uncontrolled collision cascades. The thermosphere climate index measured by spaceweather, CALM as of May 13, 2026, reads 1667 times 10 to the 10th power watts against a historical maximum of 49, 4 and a minimum of 205. It is elevated, not extreme, but elevated. The Sun is breathing on the upper atmosphere. The satellites feel it. And yet prediction remains incomplete. This is the honest core of what every solar physicist will tell you. The instruments are in place, the models are running, the observatories are operational, and the B's will remain unknown until it arrives. NOAA's Cian Lil simulation projected the glancing blow from R4436E's CME. It projected the timing, the trajectory, the possible storm level. Whether it arrived as a minor disturbance or a genuine G1 interval or something weaker, the instruments at L1 measured what actually came through. The difference between a G1 event and a G3 event is not always foreseeable from coronagraph imagery and solar wind models. The difference between an oriented CME that drives a storm and one that misses entirely is sometimes resolved only 40 minutes before it presses against the magnetopause. This is not a failure of science. This is the fundamental physics of the problem. The interplanetary magnetic field carries its orientation encoded in the structure of the ejected plasma, wound up inside it like a coiled spring during the eruption, and that orientation north or south cannot be reliably measured until the solar wind structure itself arrives at the L1 point. The question is not whether the monitoring is in place. The monitoring is in place. The question is what the data will show when it arrives. Today, May 14, 2026, as Chuan 366E's fast wind stream begins to arrive, and as the IMF environment left disturbed by the CME aftermath fluctuates in ways that no model yet built can fully resolve, approximately 8 billion people on the surface of this planet go about their lives beneath a magnetic field that represents the only shield standing between them and the continuous stream of electrically charged particles the sun has been sending outward since before there was life here to be harmed by it. The people of Troms know this. The grid operators who rebuilt Hydro's protection systems after 1989 know this. The engineers who designed NOAA's SUFO L1 observatory and placed it at the Lagrange point know this. And now the data from those instruments flows back toward Earth at the speed of light, crossing 1.5 million kilometers in 5 seconds, so that the people watching the readings have whatever minutes they have to prepare. The Carrington Event of September 1859 deposited enough energy into Earth's magnetosphere to register at negative 1760 nanotesla on the DST index, to make the aurora visible in Cuba, to set telegraph offices on fire across 2 continents, and to complete its 150 million kilometer journey from the sun to Earth. In 17.6 hours, it struck a civilization running on copper wire and coal. It did not find satellites. It did not find undersea fiber optic cables carrying financial transactions. It did not find GPS receivers guiding aircraft carrying 300 people at 35,000 feet over the Atlantic. The sun does not know any of this. The sun does not make distinctions. The coronal hole CH1366 opened. The solar wind flowed. It is flowing now. And somewhere in the 150 million kilometer gap between the sun and the planet you are standing on, a stream of charged particles traveling at hundreds of kilometers per second is crossing that distance, carrying within it the unresolved question of what the interplanetary magnetic field will say when it arrives.